Welcome to the second semester of chemistry. We have made it into the math focused semester in the chemistry course. So you'll need your calculator every single day. Luckily, it's not super tricky math stuff. It's mostly the equivalent of rigor of what an Algebra 2 class will mean. But we'll be practicing doing fun things like multiplying and dividing and plugging numbers into chemical equations and solving for variables. And yes, sig fig rounding is going to matter a lot. Now, that does not mean that we can forget all the stuff we learned the first semester of chemistry. No, we are definitely going to still need to know how to write formulas for ionic compounds and covalent compounds. Yes, we're going to be doing that all semester long. We're also going to still need to be able to have that skill of writing our own chemical equations. Remember our 5 types: decomposition, synthesis, single replacement, double replacement, and combustion. We'll need to be able to do that too and to balance them. Now we're actually going to use those chemical equations and be able to do some fun things like math based on them. So that brings us into our first lesson of the semester, the first lesson in Unit 8, which is all about the mole and chemical quantities. When I say the word quantities, that means numbers and measurement type things, which is how we study chemistry. So for today's lesson on the mole and molar mass, you'll absolutely need a periodic table. We need that every single day in chemistry, but especially today when we learn about the concept of molar mass. And oh my gosh, you guys, calculator every single day is what we will need. Okay, so let's start getting into the mole and molar mass. First, you will notice I have pictures of cute little moles on there. It's nothing to do with the animal, the mole, but I think it's a funny little term that gets students thinking, being like, well, what's the connection there? And frankly, I do not know, and I don't really care. What I care about is us knowing how to use the concept of the mole to do calculations in chemistry, because it is all about the mole. Okay, so let's back up. You're like, there's socks on the page and eggs. What is she doing? This is not chemistry. Well, let me build into this. It says scientists need a way to keep track of how much of something they have. If I'm doing a chemical reaction, I need a way to verbally represent how much of my reactants I am using, right? But just in everyday life, we use things like units to represent amounts of things. Here's some normal examples of units that you've probably heard of before. When I say a pair, you should know, oh, when you mean a pair, you mean 2, right? If I say a dozen of something, that means that there is 12 of that something. If I say you have a ream of paper, it's understood that a ream will have 500 sheets of paper. If I say I have a gross of something, there will be 144 of that item. So these things are just units. It's a way to express in words an amount of something. Okay, so let's utilize this. So how much of something? How many atoms do you think are in a copper penny? Yes, I know a penny is very small, but y'all, we know how small an atom is. And I'm like, how many atoms are in a penny? Y'all, that would be way too hard to count because atoms are super tiny. So scientists needed a way to develop our own method for counting tiny things like atoms and particles. This brings us to the concept of the mole. So what is a mole? A mole is one of these units. Y'all, it's like a pair. It's like a dozen. It's like a ream. Except when I say I have a mole of something, I don't have 2 or 12. I have 6.02 times 10 to the 23rd things. That 23rd, 6.02 times 10 to the 23rd means I get to bump my decimal that is right there behind that 6, 23 places that way. This is a ginormous number. It's known as Avogadro's number because this super famous scientist guy named Avogadro determined this number, this counting unit that allows us to count teeny tiny things in chemistry. So whereas I would have a dozen donuts, we know that would be 12. If I had a mole of donuts, y'all, that would be 6.02 times 10 to the 23rd. And I know you see a pile of donuts, you're like, wow, that's a lot of donuts. But no, this is not a great picture representation of really how big a mole is. Let me show you what I'm talking about. Y'all, I mentioned that a mole is 6. Oh my gosh, look at all those zeros. I actually had to physically type out for you guys That is just crazy, almost incomprehensible how big a mole is. So I'm going to have us watch this really fun video that kind of ties this all in together and kind of gives us a little bit more perspective of what we're really talking about when we're talking about a mole of something.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So that video does a great job of trying to explain how big of a number this actually is, but then also at the same time how useful it is, because in chemistry we are studying very, very, very small things, right? They said in the video that we had, crazy kind of examples of these with our normal everyday atoms. For example, if I had a mole of hockey pucks, or 6.02 times 10 to the 23rd hockey pucks, that would equal the mass of the moon. A mole of basketballs would fill a bag the size of the earth. A mole of pennies would cover the earth 1/4 mile deep. That's wild for these everyday objects. But in chemistry, we said we look at the small things, and we call these small things particles. So you'll hear me refer to 1 mole being equal to 6.02 times 10 to the 23rd particles. So particles in chemistry are our things that we look at. Now, a particle can actually be broken down or specified into one of 4 things. It can be an atom, it can be an ion, it can be a molecule, or a formula unit. So let's look at each one of those individual particles and kind of expand on what that actually means. So an atom here, guys, that is just me picking one thing off of the periodic table, not that one thing bonded to somebody else. So here my example is just magnesium. A magnesium atom looks like one of that element. Now an ion is also one thing, but it is a charged atom, right? And now if you'll remember my groups on the periodic table, magnesium is in group 2 with the other alkaline earth metals, and he has 2 valence electrons, and he loses those 2 valence electrons to where he forms a positive 2 charged ion. So an ion is a charged atom, but here we are, we're only looking at one element for both an atom and an ion. Now the last 2 classifications of particles are a molecule and a formula unit. We've actually seen these terms before because a molecule is a covalent compound, meaning it's made up of more than one nonmetal off of the periodic table. And a formula unit is what we used to call an ionic compound, which is made of one metal and one nonmetal, or a better way to say that would be one cation, positive ion, and one negative ion. So we've also practiced writing formulas for covalent molecules and ionic formula units. But if I see those things, those are totally a classification of a particle. So my molecule here, water is an example. The first thing I notice here is I'm like, y'all, they're made up of more than one thing from the periodic table. Yeah, I've got some hydrogen and some oxygen, 2 things. I've got some sort of a compound. They're both nonmetals, so I've got covalent molecule, okay? This next example for a formula unit, this is magnesium hydroxide, okay? It's made up of obviously more than one thing from the periodic table, and it's a compound between the magnesium cation with a positive 2 charge and the hydroxide polyatomic anion with a negative 1 charge. Keeping in mind when we're writing a formula for these ionic compounds, us knowing the charges of each ion lets us know what ratio of each ion we need to have to the other by the process of crisscross. And yes, we will review all of this again because it's been a second since we've done our chemistry formulas. Okay, so that was our atoms, ions, molecules, formula units. So now we're going to go through this practice and be like, can I recognize these based on the formulas of whether they're an atom, an ion, a molecule, or a formula unit? So for the first example, it says I have 1 mole of aluminum. And if I have 1 mole of aluminum, that means I have 6.02 times 10 to the 23rd. What of aluminum? Is aluminum, and just looking at that symbol, is that an atom, an ion, a molecule, or a formula unit? Let's see. An atom, yes. So a mole of aluminum is 6.02 times 10 to the 23rd atoms. It is an atom. One thing off of the periodic table, neutral, so no charge. The next one is a mole of sodium, I'm going to have to say it, ion, is equal to 6.02 times 10 to the 23rd ions of sodium. So still one element off the periodic table, but I see a charge, whether that's positive or negative. That is an ion, not an atom. Okay, next example is 1 mole of carbon dioxide is equal to 6.02 times 10 to the 23rd. All right, well, I know it's not an atom or an ion because it's like a formula of a compound, more than one thing. Now, all of those elements in carbon dioxide are nonmetals, so it's covalent, and we call covalent compounds molecules. So 6.02 times 10 to the 23rd molecules of CO2. And last example, 1 mole of sodium chloride is equal to 6.02 times 10 to the 23rd. Okay, so it's some sort of a compound. Now I see sodium, he is a metal, and chlorine, he is a non-metal. We've got an ionic compound here, and we call ionic compounds formula units. So that is a good breakdown of what I'm looking for when I'm looking at each one of these 4 types of particles. But if I say I have a mole of any of these 4 types, you know that to be 6.02 times 10 to the 23rd of that item. Okay, now we're going to get into the concept of molar mass, and if there is something that is like truly the heartbeat of this entire second semester of chemistry, it is molar mass. You guys are going to turn into robots to where when I say, what's the molar mass of whatever, you guys will know exactly what that means and how to calculate and how to give me that answer. And it's going to be a super powerful skill for us to know how to do. So the molar mass, I kind of like this sometimes when terms seem like they make sense or guide you to what the definition of it is. But the molar mass is the mass of 1 mole of an element. That makes sense. Molar mass, the mass of a mole of an element. And y'all's brains are about to explode. There's a real quick and easy way to find the molar mass of any element. Do y'all remember that decimally number on our periodic table? The one that last semester we said was the average atomic mass of that element, meaning the average of all possible isotopes of that element, their masses, right? It also means molar mass. Y'all, it is numerically equal to that average atomic mass right off of the periodic table. But the units are expressed in grams, not in AMU. Okay, y'all, the molar mass, whenever I say molar mass, you think decimal number on the periodic table. It is nothing crazier than that. That's the mass of 1 mole of that specific element, any element that you see. Okay, so now we're going to practice using our periodic table to figure out if we can find these molar masses. I bet we can. I'm super excited. I have my periodic table right here, right now. So if I were to ask you, well, what is 1 mole of carbon atoms? How many grams would that be? You were like, great, well, I need to find carbon first on here. And I find carbon right there. Look at its decimal number. Boom. You guys, that is how many grams are in 1 mole of carbon atoms. 12.01. Look how smart we are. Next one, a mole of magnesium atoms. Got to find magnesium. He's way over here. He's a group 2 guy. There he is. A mole of magnesium weighs 24.31 grams. Look at us. This is so fun for us. And last example, a mole of copper atoms. He's one of my fun transition metals. He is right there. Guess what? A mole of him weighs 63.55 grams. Now, this concept of the mole is really interesting because we can think about a mole being kind of 2 different things. A mole is the decimal number on the periodic table. Now, depending on what element you are, that decimal number is different. Because if I were looking at each one of these atoms individually, we know a platinum atom is going to be much bigger than a hydrogen atom, right? So we would expect for a mole, or 6.02 times 10 to the 23rd particles of these elements, to be different, right? If I have 6.02 times 10 to the 23rd particles of platinum atoms, they are bigger atoms, so they're going to weigh more. Versus if I have 6.02 times 10 to the 23rd hydrogen atoms, that itty bitty little hydrogen atom is going to weigh much, much smaller. So that's what the variation is. But when I say a mole, yes, it's the number 6.02 times 10 to the 23rd, but my masses, they're represented on the periodic table, and then they are different because the size of these individual atoms, and therefore the masses are going to be different. Okay, that was a giant tangent, but I wanted to kind of, wrap it all up nicely in a present with a little pretty bow. So my units for molar mass, since the definition is the mass per 1 mole, the units for these decimal numbers are grams per mole. So when I say what's the molar mass of manganese, well, it's 54.94 grams per mole. That's how many grams are in every 1 mole of manganese. So the molar mass of carbon being 12.01, that means there are 12.01 grams of carbon in every 1 mole. And you guys, this is such a useful understanding, because if I were to need to do something in the lab and I'm like, you know what, I need a mole of magnesium. Well, what am I going to do? Am I going to count out 6.02 times 10 to the 23rd atoms of magnesium? I'm not going to do that. That would take me my whole life, and I would not get anywhere close to that. But I can be like, okay, I've got a balance that I can measure the mass of things on. Let me just scoop out 24.31 grams. And when I get to 24.31 grams, I know that that will be exactly 1 mole of magnesium. So what a fantastic, useful skill of understanding this concept of the mole and how that means I can navigate through doing experiments in the chemistry lab without having to count out the things. Okay. You may see some other names for molar mass. You may see something called like molecular mass. That's still molar mass. Or molecular weight, or formula mass, or formula weight, or gram formula mass. We will typically in our class, since I like repetition and things to not be confusing, I will typically say molar mass for everything. But I did want to bring this up because you can also tell what the molar mass is of something that's not just an element of the periodic table. Like, what if I wanted you to give me the molar mass of like a compound, meaning something that has more than one element of the periodic table? You're like, oh gosh, am I going to really have to do that? Yes, you are. And it is actually not that tricky. We're going to get into it here in a second. But I just wanted to bring up that you do have names that suggest that, y'all, I can take the molar mass of things like molecules or formula units, okay? And so that's where you see that differentiation here in the names, is that they're kind of specifying for compounds as opposed to just single elements. But they all mean the same thing. It's still the decimal number from the periodic table. That represents how many grams are in 1 mole of that substance. Okay, so as I alluded to, the final part of this lesson today is how to calculate the molar mass for a compound, not just one thing, but more than one thing. Okay, I'm going to talk about these steps real quick, and then we're going to go through an example, and I think it'll make a little bit more sense to where you won't even have to think about the steps, which is great. So the first thing you're going to do is you're going to write, well, the correct formula, hopefully, for the compound. You're like, oh, nomenclature again. You're like, yes, we're going to have to do some nomenclature again. Yes. Step number 2, then you're going to look up the molar mass, which we now know is the decimal number, also known as the average atomic mass. Look that up for each element in the compound on your periodic table. Great, we can find these numbers. We're very smart. Then step 3 is you're going to multiply the molar mass of each element by any subscripts for that element, if any. It may not have any subscripts, and that sounds good. And then you'll add all the masses together, and then you will pop the units at the end, grams per mole. Now, since this is a math, our brains are starting to think about this is a mathematical process. Our brains are maybe starting to think about things like sig figs and roundings. But the molar mass is the mass of a mole. And if you'll notice, these decimal numbers on my periodic table, I have them rounded to the hundredths place. So as a result, if you're calculating the molar mass for a compound, your molar mass should always have 2 places past the decimal. And trust me, if you were doing things right in your calculator, your math should always show that. So that's what we're looking for. So all molar masses will be rounded to the hundredths place. All right, so now I'm going to do an example. I'm super excited about this. So this is a type of a problem that you'll be expected to do. And this will be a type of a problem that will be the simplest skill that you will have to use first in order to do harder things with. So molar mass is very important for us today. So it says find the molar mass of calcium phosphate. You cannot do anything unless you write the formula down of calcium phosphate. And y'all are thinking, well, calcium is just, like, oh, he's right here. No big deal. We got that. And phosphate, I'm sure that's like somewhere on here too. No, how do you know how many calciums you have? How do you know what you got going on there in phosphate and how many? You're like, I don't. You need to write the formula for calcium phosphate first. Oh my gosh, well, what is this? Calcium's a metal, right? So that means I'm probably doing an ionic compound between the metal calcium, who's got a +2 charge because he's in group 2, and phosphate. You guys, phosphate's one of my polyatomic ions. Let's see if we can find a phosphate. Oh, yep. So phosphate's got a -3 charge. So I would have to crisscross that calcium +2, phosphate -3 to boom. Let's see what the formula for calcium phosphate is. Yes, you should have been able to do this since I think halfway through the first semester, and we've been practicing it ever since. Now, y'all, we gotta have to have this formula correct, because if I'm gonna look at this formula and calculate the molar mass based on it, I need to know exactly how many of each I have. Okay, so we found the formula, which was the first step for calculating molar mass. Now I'm going to look at each element on here. The first element that I run into is calcium. So I'm like, okay, calcium. We already found you over here. Let's look at you again. Calcium, calcium, calcium. Well, the molar mass of one calcium atom is 40.08 grams per mole. But I got 3 of them. So that's why you see here in my calculation, I'm multiplying that 40.08 times 3. So the overall mass of all 3 of those calcium atoms is 120.24. Great, we tackled the first element. The next element we're moving on into is phosphorus. Phosphorus, let's see if we can find phosphorus's molar mass on his periodic table. It's 30.97, right? Well, how many phosphoruses do I have? I got 2 of them. So remember the distributive property of chemistry, meaning if I have a subscript on the outside of the parentheses, it gets distributed to everybody on the inside. So I do not have 1 phosphorus. I have 2, okay? So I have to multiply that molar mass, that 30, I lost him, there he is, that 30.97 times 2 to get a total coming from phosphorus as 61.94. This is a lot of work, but I'm gonna make it seem a lot easier here in a second. All right, and then my oxygens. Oxygen's molar mass is 16. That's a nice, real easy one, but I multiplied it by 8. That means there are 8 oxygens in that formula. Let's see, remember distributive property. That 2 gets distributed in. That oxygen already has a subscript of a 4, which means that I multiply those 2 numbers. 4 times 2 gives me 8, so I have 8 oxygens. So the molar mass of 16 times 8 means that oxygen is bringing 128 grams per mole to the table. Okay, so I've done that. That is all the elements in calcium phosphate. So what do I do now? Y'all, I add them up. And then when I add all of them up, I get 310.818 grams per mole. That is the molar mass of calcium phosphate. That means 1 mole of calcium phosphate weighs 310.18 grams. That also means that 6.02 times 10 to the 23rd formula units of calcium phosphate weighs 310.18 grams. Very cool. So basically all that we've done here is just we found each one of the elements and we multiplied them by how many of that element you had, adding up all of the molar masses. You're like, oh my gosh, that is a lot of work for me to write down on paper. Here's the cool thing, you guys. I'm going to require no work for showing molar mass. And the reason is that it is something that you must be able to create or produce or write down for me kind of immediately. Because I said we're going to use some math with our molar masses for other more complex stuff actually here pretty soon. So your calculator knows your orders of operations, you guys. So I can actually type that full thought process that I did here on the previous slide into my calculator as one stream of thought, okay? So just breaking it down here, and I'm going to actually show on my calculator here in a second so you can see me type, is that I'm looking at here, I would type in 40.08 times 3. That represents those 3 calciums. And then I can hit the plus. And then this over here is my 2 phosphoruses. And then plus, and this over here is my 8 oxygens, okay? My calculator knows if I were to just type that in as is, it's going to group the multiplication sections together, and then it's going to add them together at the end. So let's see if Mrs. Sabatka was right. You're all like, there's no way, Sabatka, that we can do it this way. I'm like, oh yes, there is a way. I will show you. Let's see. So I got 40.08 times 3 plus 30.97 times 2 plus 16. And yes, you guys, you do not have to type in the decimal 00, but I put it in there on my work shown for this specific example, so it looks a little bit more familiar as a molar mass with 2 places past the decimal. But anyway, I mean, I will not see the work in your calculator, so you don't have to show the 2 zeros there. Okay, times 8. All right, let's see. Woo! All right, so it works every single time. So the way that you solve for a molar mass, first you've got to write down the correct formula. You need to know that there are 3 calciums, 2 phosphoruses, and 8 oxygens in there by producing that formula. But then once you have your formula, you can boom, 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 and feel really, really good and happy and ready to go. Okay, so, and if you need to write your work out to the side, like that is so super fine. Y'all can write anything you want. I'm just saying that I am not going to expect to see work, or I will not require work to be shown. Okay, so I thought now maybe we would do some more practice problems together just so we can get nice, warm, and fuzzy on the inside, especially when it comes to you know, like writing our formulas for things like our compounds, because it's been a while and we may have forgotten. So on the back of our notes page, you guys, we have some practice problems where I'm going to have you solve for the molar mass of each one of these examples. Okay, if you'll notice, I did not give the formula for any of them. You will need to produce the formula for me, depending on whether it's ionic or covalent. And then you will need to figure out how many of each element you have going on in there and figure out the molar mass based on the decimal number of the periodic table. Okay, great. So here we go. Our first example is water. I think we probably will have no trouble at all writing the formula for water. H2O. You guys with me so far? Okay, amazing. So we know that there are 2 hydrogens and 1 oxygen in H2O. Now I'm using my periodic table, right? Okay, I know that hydrogen's molar mass is 1.01, which means I'm going to go for my calculator, 1.01. And there are 2 of him, so I'm going to go times 2. That is all of the hydrogens in H2O, right? Well, I've got a second element involved. I've got oxygen. I've got 1 oxygen. So I move on over. I'm like, oxygen, where are you at, my friend? He is right there. He's got a molar mass of 16, right? And there's only 1 of him, so I don't have to multiply it by any subscript. And I hit enter, 18.02 grams per mole. So my answer is 18.02. Noticing, whoops, you cannot see, that they're still retaining those 2 places past the decimal that my periodic table also demonstrates. But the units are so important. This is not correct. What is this, 18.02 penguins? Well, no, it's the molar mass. Well, the units for molar mass, and how'd you write it down in your notes, is grams per mole. And here's the funny thing, I didn't mention this earlier. We do abbreviate the word mole to MOL. Just chopping off the E is an abbreviation, apparently. You know, that's a lot easier, I guess, to write than the full word mole, but that's the abbreviation for mole in chemistry. But so that is my answer. Like I said, you do not need to show all of your work. Your calculator can handle that work for you, but feel free if you need more space to map out that molar mass calculation. You can totally take it. You need to have the formula, or else this is not going to be anything, right? So speaking of, on the next problem, we got to create the formula for zinc chloride. You're like, okay, zinc chloride. Ionic compound. I know this because zinc is a metal. And zinc is one of those weird transition metals that, even though most transition metals need to specify their charge with a Roman numeral, zinc is part of the silver, zinc, and aluminum arrow, where zinc has, well, silver has +1, zinc has +2, and aluminum has +3. So if it helps, you can totally write, well, yeah, zinc's got a +2 charge up here, right? Chloride is plain old chlorine. Plain old chlorine is a halogen here in group 17. Everybody makes a -1 charge, right? So the formula for zinc chloride is ZnCl2. Cool. So now I know what I'm doing here. I'm ready to go. I need to find zinc. There's only 1 of him, but what is zinc's molar mass? Zinc has 65.31. So I go 65.3. Oh, not 3.1, it's 3.8, you guys. Okay, and there's only 1 zinc in my zinc chloride formula, right? And now I got to find chlorine, and chlorine is right here. He's got 35.45. So bumping in chlorine here, 35.45. And according to my formula, there are 2 of them, so I do need to multiply that by 2. Okay, so my formula for zinc chloride, let's see, it's 136.28. So I am ready to write that down. 136.28, and the units, of course, are grams per mole. Okay, I'm going to do a couple of more just so we can, specifically get that nomenclature practice of writing our formulas, kind of, remembering all that stuff is a little bit tricky. Cobalt to chlorate. This is another ionic compound, a metal cobalt with a what charge? That's the Roman numeral, means he has a +2 charge. And then chlorate. Remember when I see 8s or ites, that's my brain being like, oh, it's one of my polyatomic ions. Let's see which polyatomic ion chlorate is. Chlorate is ClO3 with a -1 charge. So if it helps remembering for your crisscross, right? that 2 that's going to be coming from the cobalt is going to fall on the outside of the parentheses for that chlorate. So my cobalt 2 chlorate is Cl and then ClO3 2. So that's my formula for cobalt 2 chlorate. So I got a little bit more going on here. I've got one cobalt though. So cobalt, we're going to find him. He's got a molar mass of 58.93. So I'm going to get my calculator out. I'm going to write his thing, 58.93 plus. And there was only one of them. So which is why I'm moving on by putting the plus sign in. And then I've got chlorine is my next element. But careful, how many chlorines are there? There are 2 of them because that 2 gets distributed. So if you'll remember from the previous example, and I mean, you may not remember, that's okay. I just want to keep bringing my periodic table over here because I'm moving a lot of things is what I'm trying to say. But chlorine's molar mass is 35.45. So I'll say 35.45, and there are 2 of them. So I'm going to say times 2. Okay, so that's all the chlorines. Next up, I've got my oxygens, you guys. Oxygens, I have a 2 on the outside of here, and I've got a 3. So remember, we distribute that 2 in, and I'm going to multiply 2 times 3. I've got 6 oxygens. Molar mass of oxygen is 16, and I've got 6 of them, so times 6. Okay, I'm ready to hit enter, and that is the molar mass of cobalt 2 chloride. It is 225.83 grams per mole. We box off our answer so you can be like, look here, Mrs. Sabaka, I have the right answer, and I'm gonna be like, yay, good job, you did amazing. All right, let's do like 3 more. I'm feeling excited today to get back into chemistry. Okay, next one, dichlorine heptoxide. So this has got some amount of chlorines and some amount of oxygens. I'm dealing with all nonmetals here. That means a covalent molecule, which is probably why you see these prefixes in front of you telling you how much of each one of those elements you have. No crisscross here, no ionic compounds. Di means 2, so I have 2 chlorines, and hept means 7, so I have 7 oxygens. And on our new and improved reference charts on the back of our periodic table, I even wrote my prefixes here on naming those covalent compounds because I'm a nice person. All right, so I've got 2 chlorines and 7 oxygens. I'm not going to even pull out my periodic table because we've dealt with chlorine and oxygen quite a bit because chlorine's molar mass was 35.45. That's the decimal number on the periodic table. I've got 2 of him, so times 2. Then I got oxygen plus his molar mass is 16. And I've got 7 of them, so times 7 equals 182.9. 182.9. 182.9. Now specifically, my calculator just chopped off at the tens place because if I were to carry it out to the hundredths place, it would be a 0. But our molar masses are always to the hundredths place, so please write that 0 following that 0.9. Cool. So that's how much 1 mole of dichlorine heptoxide weighs. Next up, we got silver nitrate. Silver is part of our transition metal arrows of +1, +2, +3. So silver has a +1 charge. So this is an ionic compound, which means crisscross. And nitrate is a polyatomic ion, NO3, with a -1 charge. Okay, so crisscrossing those formulas, I have AgNO3. And once again, you do not need parentheses around your polyatomic ions if you just have one of that polyatomic ion. If you have more than one, like cobalt 2 chlorate did, yeah, we need the parentheses. But I love having that establishment of knowing that those parentheses will maybe help us when we take this further into writing formulas for our chemical reactions and balancing those chemical reactions. Okay, that was a giant tangent. Okay. So now we're going to find our molar mass of all of our fun things. Silver's molar mass, he is right there, 107.87. 107.87. And there's only one of him, right? So I can move on. Plus, next guy I have is nitrogen. I only have 1 nitrogen. There's not something on the outside of the parentheses that I've distributed into. So 1 nitrogen, his molar mass is going to be 14.01. 14.01. Plus, our next guy is oxygen, and I have 3 oxygens. Oxygen's molar mass is 16 times 3. Okay, so I get 169.88 grams per mole. Cool. All right. Last one I'm going to do with you guys before y'all finish the rest of these on your own and have so much fun with that. Calcium acetate. Calcium's plain old group 2 metal. All group 2 metals make a +2 charge. Acetate's that really wackadoo polyatomic ion that's like, oh my gosh, got a lot of stuff in there. Where's my acetate? Oh, he's up at the top. C2H3O2, all with a -1 charge. So that is nutso business. So C3H2O, well, what did I say? C2H3O2. It's been a break for me, you guys. Get my chemistry brain back together. Okay, so the crisscross for that, or the formula for calcium acetate, is Ca and then C2H3O2 with a 2 on the outside. Yes, I wanted to finish off with this one because there's lots of numbers to figure out each one of these elements. Okay, calcium's up first though. I have 1 calcium, so let's see. Calcium. Okay. He's got a molar mass of 40.08. 40.08. There's only 1 calcium. I'm ready to move on. Carbon is up next. Carbon's molar mass is 12.01. And how many carbons are there? Well, that 2 gets distributed to everybody on the inside. So my carbons is actually going to be 2 times 2. It's going to be 4. So there are 4 carbons in there, so I need to multiply that 12.01 times 4. All right, next element in there is I got some hydrogens. Hydrogens molar mass is 1.01. 1.01. And how many hydrogens do I have? 3 times 2? 6. So I got to multiply that by 6. And then my last element in there is oxygen. He is 16. And how many oxygens are in there? 2 times 2. So times 4. Lots of stuff going on in there, but your calculator, he's understanding. He's like, yes, I got this. I got you. I'm ready for giving you the answer. And the answer is 158.18 grams per mole. So 158.18 grams per mole. Amazing. So there you go. A mole is just a unit in chemistry. It just happens to represent a lot of things, specifically atoms, ions, molecules, or formula units. And yes, there is Mole Day. Mole Day is October 23rd, and that's where you get the 10, which is the 10th month of the year, times 10 to the 23rd. So I really do hope that everybody celebrates Mole Day. It's one of my most favorite days in the year. So yes, you guys, a mole is a unit. We learned about molar mass today and how to calculate that from the periodic table. And we are ready to use this molar mass and the idea of what a mole is to move on and do some more fun calculations with it with molar conversions.